Hey everyone, I'm Akash Joshi, I'm the OR Guru, and today we're going to be talking about linearizing functions. Specifically, we're going to be talking about absolute value functions. Alright, now let's talk about the problem. There are 172 popsicles and you would like to split them evenly among two people. Keep in mind that this is an extremely simple problem and it's not something you would use using an operations research mathematical model, but just for the purposes of explaining how to linearize functions, we're going to use this problem. An actual problem using linearization and dividing up evenly, like allocating equally, would be fairly dividing up an unknown value and minimizing something according to that value. Alright, so back to the problem. Let xi be the number of popsicles each person gets. I equals 1 and 2 because there's a first person and a second person and there's only two people. And this is our decision variable, xi. Let's talk about the formulation now. Alright, so we're going to minimize the absolute value of x2 minus x1. This is the difference between the number of popsicles that each person gets. And of course, it has to be absolute value because the second person could get 0 popsicles and the first person could get 170 popsicles or 172 popsicles. And that would be a difference of negative 172. And we don't want that because that's not even. So it has to be absolute value. And that's what we're trying to minimize, the absolute value of the difference between the number of popsicles each person gets. Okay, now let's look at the constraints. X2 plus x1, number of popsicles each person gets, has to be 172. That makes sense. And of course, the number of popsicles each person gets has to be positive for both people. Okay, so let's talk about the problem with this formulation right now. You could use this formulation if you wanted to, but it would be pretty complicated for your computer. Okay, so nonlinear programs, which is what this is because it has an absolute value function in it, nonlinear programs suck. You know why? It's because it takes the computer forever to solve. If we want to simplify this problem, we can always convert it to a linear program. Alright, so let's talk about converting it into a linear program using linearization. First, we're going to set our new variable y equal to the absolute value difference. So instead of minimizing the difference straight up, we're going to minimize y. We're going to minimize y, have the same constraints, and in addition, we're also going to say y is equal to this right here. All right, so that's pretty simple. It's pretty much the same thing. Let's get into the next part. Okay, now what we're going to do is we are going to set y greater than or equal to x2 minus x1, or the absolute value of that. And the reason we change it from an equal sign to a greater than or equal sign is actually because this is just a step in the process of trying to get rid of the x2 minus x1. And what we're arguing is that the optimal solution won't change if you change it from an equal sign to a greater than or equal to sign. The only thing that will change is the feasible region, but the optimal solution should stay the same. And we'll probably get a little bit more in depth about why we change it from an equal sign into a greater than or equal sign sometime later, or sometime in a different video. Okay, let's linearize the absolute value function now. So first we need to understand that the absolute value of x2 minus x1 is the same thing as maximizing the function x2 minus x1 and the function x1 minus x2. So what do I mean by that? Let me show you a graph so you can understand a little bit better visually. Alright, so over here we have x2 minus x1, and over here we have x2 minus x1 and x1 minus x2 graphed, and this is the absolute value of both. We both only care about this. And remember, when I say x2 minus x1 is graphed, this is just an approximation of how the graph looks like. It's not accurate because, of course, we don't know what x is, but that's pretty much how the absolute value function looks like. And then when we maximize two functions, so first first we have, so let's look at the absolute value of x2 minus x1. That's the same thing as graphing two parts of an equation of two functions. So the first part of the first function is this little part, the second part of the second function is this little part. So we can break up x2 minus x1 into x2 minus x1 and x1 minus x2, and then we can find the highest value for each of the x values in this function. So when we graph x2 minus x1 and x1 minus x2, we just get something that looks like this. Okay, so when we maximize it, what maximize means is that for every x value, we're going to take the highest y value for each x value. So for the x value, let's say x equals 5, we're going to take this y value and not this y value. So eventually we just get something that looks like this, which is the same thing as our absolute value function. And now let's talk about resembling a maximum function in like mathematical terms. Okay, so back on this slide, we figured out that y is greater than or equal to the absolute value of x2 minus x1. And since the absolute value is equivalent to this maximization function, we can say that y is greater than or equal to the maximization function. And we can divide this up into y is greater than or equal to x2 minus x1, and y is greater than or equal to x1 minus x2. Okay. Next, finally, we have our formulation, our compact formulation. So we're going to minimize y as usual. We have the constraint that there has to be 172 popsicles, and number of popsicles each person gets has to be positive. And then we simply have this over here to ensure that we are defining y correctly. And now, if you notice, there's no absolute value sign in this formulation. There are simply equalities and inequalities. And yeah, so this formulation right here is the same thing as if you just minimize the absolute value of x2 minus x1. And the reason why we're making it a linear program is because, remember, linear programs are extremely simple for computers to solve, and they can get you an answer in a matter of seconds, whereas nonlinear programs could take up to like hours if the programs are big enough. So yeah. Okay, that's it for today. Thank you for watching. Have a great day. Goodbye.